we're asked to find the limit as x approaches infinity. If we take a look at the graph of the rational function here on the right, notice as x approaches infinity, or as we move to the right, it appears like the function value may be approaching 0, but that's not actually true. Let's work on determining the limit analytically. Notice the rational function is given in factored form. Even though the factor of 3x minus 3 does have a common factor of 3 here, there are no common factors between the numerator and denominator, and therefore the factored form is not going to be helpful. We're actually going to start by multiplying the factors in the numerator and the denominator. So we have the limit as x approaches infinity. Multiplying in the numerator, we first distribute 11 into the second binomial, and then distribute negative x into the second binomial. 11 times 11 is 121. 11 times 10x is 110x, giving us plus 110x. Distributing negative x times 11 is negative 11x or minus 11x. And then we have negative x times 10x, which gives us minus 10x squared. And now we multiply the two factors in the denominator. So we distribute the 3 into the second binomial, and then distribute the negative 3x into the second binomial. So 3 times 4 is 12. 3 times 11x is 33x, giving us plus 33x. Distributing negative 3x times 4 gives us minus 12x. And then negative 3x times positive 11x gives us minus 33x squared. And now let's combine like terms and write the terms in descending order. In the numerator we have negative 10x squared, and then 110x minus 11x gives us plus 99x, and then we have plus 121. In the denominator we have a negative 33x squared, and then 33x minus 12x gives us plus 21x, and then we have plus 12. At this point, we can use the degree of the numerator and denominator to determine this limit. Notice how the degree of the numerator and denominator are the same. They're both 2, and therefore the limit as x approaches infinity is equal to the ratio of the leading coefficients, which in this case would be negative 10 over negative 33, or 10/33. A summary of the shortcuts are shown here by determining the degree of the numerator and denominator. In our case, the degrees were equal, and therefore the limit of the rational function is the ratio of the leading coefficients. Another way to find the limit from here would be to follow the general guidelines for finding limits at infinity of rational functions, which at this point we would divide each term in the argument by the highest power of x in the denominator, which means we would divide every term in the numerator and denominator by x squared. And let's also show that. So we'd have the limit as x approaches infinity of, again, we're going to divide every term by x squared. And now simplify as much as possible. X squared divided by x squared simplifies to 1, giving us minus 10. X divided by x squared simplifies to 1 factor of x in the denominator, giving us plus 99 divided by x. Nothing simplifies here in the third term. We have plus 121 divided by x squared. In the denominator, again, x squared divided by itself simplifies to 1, giving us minus 33. X divided by x squared simplifies to 1 factor of x in the denominator, giving us plus 21 divided by x. And for the third term, nothing simplifies. And now as x approaches infinity, 99 divided by x approaches 0. 121 divided by x squared approaches 0 because the numerators are constants and the denominators are getting larger and larger. And the same thing is true for 21 divided by x and 12 divided by x squared. So all the terms go to 0 except negative 10 and negative 33, which gives us negative 10 divided by negative 33, or 10/33. Either way we approach this, notice how the limit is not equal to 0, which it may appear from the graph. I hope you found this helpful.